I believe you guys should have a copy of it. It might not be very clear on the board, but I believe you guys have a copy. I posted it, so if you go to your Blackboard, you will probably see it better and read better.
Pretty much every Friday and Saturday is when the track team competes. I'm not competing because I broke my ankle, but I will be next week.
Oh.
Yeah.
Okay. And then next week is an exam. Oh, okay. So we'll take care of it. Yeah, I'll take care of it. So you're in the same team with Zila, right?
Yes.
Zila,
No,
is it Ben? I don't know.
Beard, Bill,
Yeah,
Beard? Yes.
Yeah. Oh, talking of which, Jillian is supposed to know the certain things, but I've never seen it. Yeah, I need to send him again. Oh, you guys will bring a medal this year again.
I hope so too.
Yeah, last year you guys won, right?
Yes, we're actually getting our rings today at the basketball game.
Oh, for last year?
Yes.
Oh.
I just got the rings.
Oh, okay.
So, come to the basketball game, we get our rings.
Halftime too?
Yes.
Yeah, that's cool. Did you guys fly to places like Texas or you still?
It's only a few people that fly out there. It's not the whole team. It's like 2 or 3 people.
2 or 3. But most of these places around Virginia, you all go to fly.
Yes.
The ones that really fly only a couple of places.
I was going to send you that song at midnight. I was going to send you that song at midnight.
Were you guys able to have something?
Not yet.
Really help you with training.
The top said C5, H12 over the NMR0123.
Yeah, not too much. No. That's not enough.
Well, like the thing says C5H8.
Oh God, Zico. Undeniable. Probably the next of those spot on animal. Should be C5H8. Okay, C5H8. The problem, I have a problem. Correct this. This should be C5H8O, not C5H12. Okay. So this is a correct formula here, C5H8O.
The integrals in those peaks add up to 12, I believe.
That's the problem of 8 a.m., right? Okay, let's solve this problem together, guys. Let's solve the problem. So the good news is that from the question, we're told that it's an alcohol. Okay? The question says an alcohol, so we have an OH over there in the molecule. And now the OH, if you look at the signal around 2, it's a kind of very tiny signal. Usually those are the signal of the hydrogen connected to oxygen, okay? So that one H there represents this hydrogen connected to oxygen. Now we have to determine the remaining structure. The integral are quite clear. The integral for the first signal around 1 indicates that we have a CH3 in the molecule. The integral next to it of 6 indicates that we have 2 CH3s that are chemically equivalent. Okay, that's the integral of 6, meaning we have 2 CH3s that are chemically equivalent. Then the next integral says 2 hydrogens, and so it means we have a CH2. Does that make sense? So those are the fragments. Now we need to connect those fragments together. And we'll connect those fragments together by looking at their multiplicity. Okay, so if I look at the multiplicity for the first signal, it's a triplet. This multiplicity is a triplet. It means that CH3 is next to a carbon with 2 hydrogen. Does that make sense? That's why it has a triplet. It means the first CH3, this guy here, is standing next to a CH2. That's why this CH3 gave rise to a triplet. And if you look at this quartet over here, that's a quartet. It simply means that it's standing next to a CH3. So this CH2 is standing next to a CH3. it definitely means that on this other side of the CH2 should be a carbon without hydrogen. Does that make sense? It should be a carbon without hydrogen. So it will simply be a C. Because if you have a carbon with a hydrogen here, then this will not show as a quartet. Does that make sense? So because it's a quartet, it means that it's a carbon without hydrogen. Yes? Say that again. Yes, let's go back. Let's start back from, at least with all the, I hate using Office with this thing. It doesn't work like the other application. So up to this point, we are all good, right? Determining the different fragments that we have in a molecule. Up to this point, we are all good, right? We know that in our molecule, we have a CH3, we have two CH3s that are chemically equivalent, and we have a CH2. Then this is the OH, because the question told us it's an alcohol. Is that okay? Yes. Integral of 6. Is that okay? Integral of 6. So up to this point, I think we are all okay, right? We are all good. Now, let's look at the multiplicity. This is a triplet. This is a singlet. And this multiplicity is a quartet. Does that make sense? Those are the multiplicity. Singlet, triplet, singlet, quartet. Now, a triplet simply means that you are adjacent to a carbon with 2 hydrogens. Does that make sense? A CH3 that gives you a triplet simply means that it is adjacent to a carbon with 2 hydrogens. That's why you have a triplet. Is that okay? So, you will have, yes, a CH3. That is a triplet, simply means it's adjacent to a carbon with 2 hydrogens. Are we good up to this point? So, this CH3 here, I will call it A, because this will be my A, that will be my B, and that will be my C. So I will call this A. So if A is a triplet, it means that A is adjacent to a carbon with 2 hydrogens. Does that make sense? Now let's look at a quartet. I will skip B. Let's go to C. If we look at a quartet, the CH2, we know that a quartet is a CH2. And for that CH2 to be a quartet, based on the fragments that we already have in the molecule, based on the fragment that we already know. Okay, because the only option we have for you to be a quartet is to be next to a CH3. There are 2 ways for you to be a quartet, right? You can be next to a CH3, or you can be next to a CH2 and a CH, so that the total number of hydrogen next to you gives 3. But we don't have a CH in here, based on the different fragments in the molecule. We know we don't have a CH in here. And so, the only option we have is that it is next to a CH3. Does that make sense? So that is next to a CH3. So that's a partial structure. That would be C. If it is next to a CH3, it means that the carbon here should bear 0 hydrogen. Does that make sense? That carbon should bear 0 hydrogen. Because if it has any hydrogen, that will change the multiplicity of the other guy. Are we good up to this point, guys? Okay. Now we need to take care of the singlets. We need to take care of these guys. They are chemically equivalent, they are singlet. If they are singlet, it means that the carbon adjacent to it should also bear 0 hydrogen. Does that make sense? That's the meaning of being singlet. It means the carbon next to them should bear 0 hydrogen, and they have the same chemical environment. In other words, they should originate from the same carbon. And this carbon here, we already know is a carbon without hydrogen. So most likely they are connected to that carbon. So I will have the first CH3 here, and I will have the second CH3 here. What is missing in the structure? The OH. So I simply connect the OH there. Does that make sense? And so the final structure for this molecule, if you want to draw it in a more fancier way, you know, will most likely be, oops, probably it was too fancy. Yeah, it was too fancy. Let me correct it. I will change this thing. OH and that. Yes. Any question? 2-methyl butanol or butanol. 2-methyl butanol. That would be the name. Let me start from here. Yes.
So you said that singlet is a carbon that can't be next to any hydrogen, but it's connected to BC is
No, these are the two CH3 that gives rise to the singlet.
Oh.
And it means that they are next to a carbon without hydrogen. So this carbon doesn't have any hydrogen. Does that make sense? Another question, yes.
What did you make the CH3 from all the elements from the CH3?
CH3 and then two CH3 without the equivalent and then the CH2. So those are the fragments that we need to combine it together.
And then the one that was the...
This one is for that guy. OH. So we're told the question said it's an alcohol. Okay. Question said it was an alcohol. Any other one? Yes.
So even though like the carbon by itself wasn't
well, because the carbon by itself, you cannot see it on the proton NMR. It doesn't have any hydrogen. But if you had a carbon 13 NMR, that carbon will probably show. Like maybe the next question will answer will have some carbon 13.
So even most of these know that that's a triple or whatever to make it carbon.
So what other way will you be able to connect the CH3 so that it should make a singlet, given the scenario that you have at hand? You know, given the fragments that you have at hand. So everything happens with what you have at hand. Remember, we started by collecting all the different fragments we know are present in the structure. And that's like a puzzle game. You need to put those fragments together, following the spectrum that we have. We'll do more examples. Yes.
So did you know that anything is an OH and not, but could it potentially that one is PhD because it's an alcohol, like maybe just run out of carbon?
If it was not an alcohol, then that would probably be a different problem. Okay. Yes, that would probably be a different problem. Let's hope that maybe we'll be able to see something that can answer that question in the future. So does that make sense, guys? Well, I know it might not make sense. Yes.
Okay, so B is more shielded than C, but
Oops. These are all B's. Yes.
oh, never mind, that makes sense.
This is the next one, CH4H9Br. We need to determine the structure for this one. You guys have a copy of that on Blackboard, so if you cannot read on the board, try to download it even with your phone and read better. Okay, because, yeah. C4H9Br, we need to determine the structure. So I will give you guys 2 minutes again. 2 minutes to try to figure it on your own before we do it together, okay? Take some time and try it on your own before we do it together. Right? I have a YouTube video, so you can watch the video. I'm doing it more. Now it's good because you will learn twice. Yeah. You will learn twice. Yeah. It's easy, right? I'm bored. Friday, we are celebrating 100 days. Celebrating 100 days. But for some of you, it will be 200 days or 300 days. 300 days. It will be a 300 day celebration. So it means that it doesn't concern you at all. At all. It doesn't concern you. Huh?
It's a school-wide celebration.
Yeah. It's not, there's nothing like school-wide celebration. If you don't pass my class, you will not celebrate at all. That's just a fact. But if you don't pass my class, there's no 100 day celebration for you. So if you stay in my class and pass my class, then you're guaranteed to have a 100 day celebration. You know? So you notice that this problem is a little bit different, right? We don't have integrals. The integrals are values are not given to us, so we'll have to solve it without the integral. And there is really no specific technique for solving this kind of thing, you know. The molecular formula is a small molecule, C4H9Br. So you might adventure yourself by probably writing out all the different isomers of the molecule. That's one way you can approach the problem. Okay, one way you can approach the problem, because it's a small molecule, C4H9Br, you can decide to write out all the different isomers of that molecule and then match them with the spectrum and see which one matches correctly. Does that make sense? That's one way you can approach it. Another way you can approach it is by using the multiplicity or the splitting pattern. You know that, okay, if one gives me a triplet, it means that it's most likely next to if this is place. So you can now do all those kind of considerations if you want to. Does that make sense? So I think I will go with the first option. I will want to put down all my different isomers. That's the option I will choose to solve this problem. Okay. Since it's a C4H9Br, the easiest isomer that comes in mind is this guy. Okay. That's one isomer. Just a straight chain and then add the Br at the end. Then the other isomer that can come in mind is by switching the position of the Br. I have that isomer also. That's a possibility. Okay? That's a possibility. So let's see again. There are other isomers. Let's see. What about having... That's another isomer, right? Does it look good? Yeah, it looks good. Any other one? Any other isomer do you know? Can we have any other isomer, guys? Let me know. Any other one? Yes, right? Yes, maybe. Let me change the ink. We can have that one. Does that make sense? So I guess those are all the 4 types of isomers we can have with that molecular formula. The blue, the black, the green, and the red. Okay? The blue, the black, the green, and the red. So we can use them to distinguish the spectrum. So if we go with the blue, let's start with the blue, the first one. How many signals do you expect to see in the spectrum? With the blue, I will have 1, 2, 3, 4. So with the blue, I expect to have 4 signals in my spectrum. With the black, how many signals do we expect to have? 4 signals, okay? The green, how many signals do we expect to have if we have the green? How many signals do you expect to have with the green? With the green, if the green is the correct spectrum, we expect to have 1 signal. This CH3, 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 they are all equivalent. All these 3 CH3s are all equivalent, and that's it. Nothing else. So with the green structure, you expect to only have 1 signal. Yes? Well, but those 3 CH2s are not the same. There is one that is connected to bromine. There is one that is connected to 2 other CH2. And there is one that is connected to a CH2 and a CH3. So they are all different types of CH2s. Is that okay? Yeah. The fourth structure, the red structure, how many signals do we expect to see there? 3 signals, okay? So we can proceed by elimination, right? Our spectrum shows us 1, 2, oops, let me not do it that way. It shows us A, B, C, and D. So the spectrum shows us 4 signals. Is that okay? Are we good up to this point? Yes. So we are left with the blue and the black. Which one is the correct structure? The black one. Does that make sense? So the black will be the correct structure. And then you can now match it with the multiplicity. You cannot match it with the multiplicity and label them. Which one is A, which one is B, which one is C. Now, if you look at A, the multiplicity of A is over here. It's a triplet. And if A is a triplet, it means that it is next to a CH2. Does that make sense? So, this would be A. Does that make sense? Now, the next signal, B. B is a doublet. B being a doublet, it means that it is next to a CH. Is that okay? It means it's next to a carbon with 1 hydrogen. That's why it's a doublet. So B being a doublet, this will most likely be my B. Let me draw it out. Let me draw that structure out here clearly so everyone can see. So this will be my A, okay, because it's a CH3 next to a CH2. That's why it gives me a triplet. Now B gives me a doublet, meaning that B is next to a CH. And so this will be my B, because this is a CH over here. Is that okay? C, if we look at C, C is, what is it? How many signals do we have there? 5. C is a quintet. A quintet means that it is next to 4 hydrogens, adjacent to 4 hydrogens. And there are 2 possibilities being adjacent to 4 hydrogens. You can be CH2, CH2 on either side, or one side is CH3, then the other side is CH. Does that make sense? But it turns out that this will be my C here. So that on one side I have a CH3, and on the other side I have a CH. Does that make sense? And if you look at D, D is how many? 1, 2, 3, 4, 5, 6. Okay? The sextet, and that will most likely be the guy. Because he's next to a CH3 here and next to a CH2. That gives him 5 hydrogen. 5 plus 1 gives you 6. That's why you have a sextet. Does that make sense? So we are able to match now the structure to the spectrum. Yes? How the black was correct instead of the blue. Now let's try to match the blue. Let's look at the blue. If we look at the blue, okay, this first carbon here is a CH3. He is next to a CH2. Does that make sense? So the multiplicity for this carbon should be a triplet. If you look at this CH2 here, he is next to 2 to a CH3 and a CH2, so a total of 5 carbons. So the multiplicity should be a sextet, right? Because that would be 6. This other CH2 here is next to 2 CH2, that's 4 carbon. What would the multiplicity be? 5, okay? That would be a quintet. I will put it as a capital Q. And the last one here is next to a CH2, so what should the multiplicity be? A triplet. So in terms of multiplicity, if the blue one was correct, you will have, oops, you cannot even see. You will have a triplet, sextet, quintet, triplet. That would be the pattern of multiplicity, and you see that it doesn't match what we have in there. Does that make sense? So you can proceed by elimination that way. Yes, Jasmine.
How would you like match the different what could be, why is it that the other elements that you like
Repeat again.
Why is it that you do the substitute where it is?
Need the black structure?
Yeah.
Then I label my B here.
Why?
Well, from the spectrum, this is the signal of B, okay? When you blow out, that's the signal of B. And that's a doublet. This is a doublet. And the doublet simply means that they are next to a CH. Okay? They are next to a CH. And when I look at this structure, the only carbons that are next to CH are this one and that one. But if you consider this one, it's also next to another CH3. So this one will never give you a doublet. Does that make sense?
Yeah.
And so the only option you have now is this guy. So that's why this is my B. Does that make sense? By matching. Yes?
When you label, like on the things A, B, C, D, does it always go from the one?
Yes. It's conventional, okay? A is always the most shielded, and then you now start from there. So you label it on the spectrum and then match it to the structure. You don't label on the structure and match the spectrum. Is that okay? You label it on the spectrum and then match it to the structure. Does that make sense, guys? So those are different ways in which you can come out and determine the structure of the molecule with NMR. 9.44. 9.44 is a combination. In 9.44 we have a proton NMR, we have a carbon NMR, and we have infrared. So we are given 3 spectra, and we need to combine the information from all 3 in order to come up with the structure. Okay, we need to combine information from all 3. It's not possible for me to put all of them at the same time on the board, and I guess you guys will have the information with you. So go ahead and try it yourself first before I jump in.
Is there a way to zoom in on the signal?
Say that again.
The proton NMR signal, they're really like it's difficult to count them.
To count the peaks.
Yes.
So you want me to give you guys this thing, the multiplicity?
Yeah.
So this would be a singlet. This is a doublet, this is a doublet, this is a doublet, and this is considered a multiplet. But from the way I see it, it's a septet, meaning 7 peaks. Okay? It's a multiplet, but the way it's displayed, I would strongly believe that it is made up of 7 peaks. So you have a proton, you have a carbon, and you have a IR. So I will give you guys some time to digest it before we solve it together. Try it on your own first. Oh, it's not even 9 o'clock. My problem is that you don't have to look for more problems. No.
It's called
No, it's impossible. Never say impossible. Yeah. You have an infrared spectrum in this stuff. So if you suspect the alcohol, go down to the infrared spectrum and see. Yes, you can. So that's why I said pull it on that one. So if you suspect an alcohol, go down to the infrared spectrum and see if the alcohol is actually present or not. Okay, guys, let's answer this question. Let's answer this question. Now, a couple of things we need to make clear here. Okay. The more spectra you actually have when you do structure determination, the better the stuff, the more easier it becomes when you have more things to look at, to collect information from. Now, if you look at your NMR table, because you guys will be given, or I was supposed to post it even on Blackboard. Yeah, the cheat sheet that will give you guys in the exam, the data sheet that will give you guys in the exam, okay? Or even what I did in class. When I was teaching in class, there are some protons, there are some signals in the spectrums that are of particular interest. You remember I said in this class that we'll be working mostly between 0 and 8. Do you remember that? I said it once in class. That we'll be focusing mostly between 0 and 8. And that very few signals go beyond 8. And if you have a signal beyond 8, you can easily suspect what you have in your molecule. So we have a signal that goes beyond 8. There are only 2 functional groups that we've done in this class that can give us signal beyond 8. What are those functional groups? You can even open your note and check, okay? If you have a signal beyond 8, you can either have an alcohol or an aldehyde. Is that okay? You can either have an alcohol or an aldehyde. When you have a signal beyond 8, it can either be an alcohol or an aldehyde. That's what I want you guys to take note, okay? That's what I want you guys to take note. You know what the aldehyde is. That's the aldehyde, and this will be the alcohol. Does that make sense? So, when you have signals beyond 8, those are the 2 things you suspect. Now that you suspect those 2 functional groups, what would distinguish them? What would be the tiebreaker, or what would be the, how do we call it, the deal breaker? Let me call it that way. What would be the deal breaker between an alcohol and an aldehyde? What do you need to do? What will help you to do that? Yes. You look at the IR spectrum, exactly, that's what she said. Okay, because you are suspecting the presence of 2 functional groups. Now you go down to the IR, that's the guy that will split them up. Yes. When you have a signal beyond 8 in the proton NMR, okay, in the proton NMR, signals beyond 8 can either be an alcohol or carboxylic acid or an aldehyde. Does that make sense? It can either be a carboxylic acid and aldehyde. And you remember, check your note. If you check your note, you will see it there. I gave you guys that on the table. Is that okay? And because you're suspecting those 2 functional groups, you have to distinguish them. You have to be sure which functional group is present. What you simply do is go down to the infrared spectrum, and that's the guy that will separate them. If you have a carboxylic acid in there, if you have a carboxylic acid in the molecule, how should the infrared look like? You remember? The infrared around 3500, you will see a broad signal. Does that make sense? If there is a carboxylic acid present, then around 3500, you will see a broad signal there. And there is no broad signal. We don't have a broad signal. So we don't have a carboxylic acid in there. Does that make sense? So, no carboxylic acid. The next guy we're suspecting is an aldehyde. How can we confirm the presence of the aldehyde? Let's look for the carbon double bond oxygen signal. You remember we did that. That signal from your table of data appears around 1700. I will post a table of data so that you guys can familiarize yourself with. Okay, I'll post it on Blackboard. That signal is usually around 1700. So if I go around 1700, I see a signal there. Does that make sense? I see a signal around 1700. Then I now know I have an aldehyde in there. Does that make sense? Go back to my proton. According to infrared, I have an aldehyde in my molecule. Is that okay? I am certain I have the aldehyde. Remember, the most important, we're building up the fragments, and we need to put those fragments together. Does that make sense? Now, integration of 6. It means I should probably have 2 CH3s that are chemically equivalent. Does that make sense? An integration of 1 over there, it means I have a CH. Is that okay? Then the integration, 2 hydrogens, 2 hydrogens. You need to be careful here. Look at where that NMR occurs. Look at where that is. It's between 7 and 8. Again, if we go back to the note, between 7 and 8, what is that? What is between 7 and 8? We suspect a benzene ring. Does that make sense? You remember that, right? No, you guys don't remember it. You guys don't remember it, I know, because you're all looking at me as if I'm coming from space. Andrew Yang says he will declassify all alien information. So if you vote for him, then you guys will probably be seeing aliens every day. Yeah, that's what he says. So, you know, I'm not campaigning for him, but I'm just telling you what he said. Okay, so don't quote me. Yes, I'm just saying, I'm just repeating his words. So I'm not yet an alien, so he hasn't declassified me yet. I'm still classified. Please, okay? There are regions in the NMR spectrum. I will repeat again. There are regions, the NMR spectrum is divided into regions. If you check your note, I gave you a table. Let me go back to the note. Before we answer this question, let me go back to the note and show you the table I'm talking about. This is the same table here. This is the same table, but this is the same table for a carbon NMR. This is the same table for the carbon NMR. It is divided into regions. So in the carbon NMR spectrum, if you see a signal between 150 and 200, it most likely means that you have a carbon double bond oxygen. That is if you look at the carbon NMR spectrum. Does that make sense? If you look at that carbon NMR spectrum and you see signals between 100 and 150, then it most likely means that you have either a benzene ring or a carbon-carbon double bond somehow. And so that's why I say the spectrum is divided into regions. That is it for the carbon NMR. If you go back again earlier on your note, where are we? You will see the same table or similar table for the proton NMR. That was way long. I understand that you guys probably must have forgotten it. That was in the study of past events. Here, that's a similar table. I can see my writing. It means that I actually talked about it. And I will repeat myself. So, the spectrum goes from 0 up to 12. And I told you, whenever you have something in the region between 7 and 8, in that region, then you suspect the presence of a benzene ring. Does that make sense? And then when you have something beyond 9, you can either have carboxylic acid or an aldehyde. Does that make sense? And so we're able now to cross out the carboxylic acid because the IR doesn't show us any OH signal. Does that make sense? And so the only thing now we are sure is present in our molecule is the aldehyde. Is that okay? And then we are also sure that our molecule will have a benzene ring because we have a set of signals in that region. And you can double check your confirmation by looking at the carbon element. Yes, question?
So, you said that the benzene ring is between 7 and 8 or because there are signals
Because there are signals between 7 and 8. Okay? Because there are signals there. And so you can double check those signals. You can double check them. So the signal here means that I have a benzene ring. That's, it's an indication that that ring is present. Yes? The carbon NMR tells you the total number of carbons in the system. We'll get to that. Okay? We'll get to that. So we can label this guy A, B, C, D, and E. Okay? So by labeling them A, B, C, D, and E, it means that we have 5 different types of hydrogen present in our molecule. Is that okay? 5 different types of hydrogen present in the molecule. Now, if you look at the carbon NMR, we can do the same kind of stuff. we have a signal here. Remember, we said signal between 150 and 200 means that you have a carbon double bond oxygen, right? That's why that table, the table I said you should familiarize yourself with. It means that you have a carbon double bond oxygen. And you see that it confirms what we have in the proton, and it also confirms what the IR shows, okay? And then from that same table, it says signal between 100 and 150 indicate the presence of a benzene ring. Does that make sense? And this is where things are important in this carbon NMR. Indicate the presence of a benzene ring. But then the carbon NMR gives us further information. It will tell us how that benzene ring is. It will tell us how the benzene ring is substituted. Because this carbon NMR means that there are 1, 2, 3, 4, okay, chemically equivalent carbons in the benzene ring. There are 4. Benzene ring is made up of 6 carbons. Is that okay? The ring is made up of 6 carbons. But when you look at the carbon NMR signal, you only have 4 signals. It means that in that ring, some carbons are chemically equivalent. That's why they give the same signal. Does that make sense? Is that okay for everyone? They give us the same signal because some of them are chemically equivalent. And then the carbon NMR goes further and tells you that among those carbons, 2 of them doesn't have any hydrogen. So they don't bear any hydrogen. 2 of them, they don't bear hydrogen. So they are basically C's without hydrogen. Because remember, in the benzene ring, all of them will probably have 1 hydrogen. But the carbon NMR tells you that there are 2 of them without hydrogen. It means that you have a di-substituted benzene ring. Does that make sense? Di-substituted means you have 2 substitution on the ring. Yes, I still have 15 minutes, so you guys have the time to digest that. Yes, let me see. Does that make sense for everyone? Absolutely. More than being sure. It still doesn't make sense, right? What was the question? The question is this. A benzene ring is made up of 6 carbons, right? A benzene ring is made up of 6 carbons. So normally you should expect that between the region of 100 and 150, you should see 6 different peaks. Does that make sense? But because we see less than 6 peaks, it means that there are some carbons that are equivalent. So because if you're equivalent, you will show 1 signal. Does that make sense? So because we have that, it means that there are some carbons that are equivalent. First thing. Now, second thing, the carbon NMR tells us that we have 2 carbons that are substituted, meaning the C's without hydrogens. Carbons without hydrogen, it means that there's a certain group, another group other than hydrogen, connected to those carbons. Does that make sense? Is that okay? Yes. We don't know. We don't know yet. Is that okay? All we know is that there are 2 groups connected to that benzene ring. Is that okay? So, those connections, I will now come in with a different proposal. Those 2 groups, I can have one group there and then I can have another group there. That's a possibility of connecting the 2 groups, right? Then, another possibility for connecting those 2 groups, guys. I can have one group here, then I can have the other group here. Is that okay? Another possibility for connecting the groups. I can have one group there, and I can have one group here. Let me call them structure 1, structure 2, structure 3. Those are the only 3 possibilities. of connecting two groups to the benzene ring. Does that make sense? Is that okay, guys? Huh? Now we have to choose between 1, 2, and 3, which one we think is the correct way of connecting those two groups. We don't know what those groups are yet. Between 1, 2, and 3, we need to choose which one we think is the correct way of connecting those rings. And we can choose those based on the proton NMR or the carbon NMR. It all depends on you. Does that make sense? Choose any of the spectrum to decide which one represents the best connection. Okay, Trinity goes with the first one. Trinity says she thinks it's the first one. Let's look at the second one. Let's start with the second one. Okay? Let's start with the second one, guys. Are we good? Let's start with the second one. Okay, if this is the second one, around the aromatic region in your proton element, this is the aromatic region, right? Okay, if we consider this second structure, this proton here, what should be the multiplicity of this proton? Someone at the back, someone at the back. What is the multiplicity of this proton here? Colin, what is the multiplicity of this proton? Singlet. Does that make sense? She says singlet. I go with her. So that's a singlet, right? But the question is, on the proton NMR in that benzene region, do you see a singlet there? You don't have a singlet in there. Does that make sense? There's no singlet in that region. In that region, we only have two doublets. This proton here has no neighbor. No, we already know that X and Y are not H's. Because the carbon NMR said there are two carbon without H's. And those H's were replaced by X and Y. We don't know what the X and Y are. Does that make sense? So we know that guy is a singlet. And when I look at the NMR, I don't see any singlet in there. So this guy is out of the game. Yes, sir. On the NMR, this singlet here, no, that singlet was assigned already to the aldehyde. We are done with this singlet, right? We are done with this guy. Because we already know that it's that guy over there. Does that make sense? We are done with it. So structure 2 is out of the game. Structure 3. Let's look at structure 3 and see. Let's look at structure 3. I'll just go as fast as I can, okay? This guy here, let's look at that guy there, that hydrogen over there, the starred one. What should be the multiplicity of that hydrogen? This one. What should be the multiplicity? There's a hydrogen here, and there's a hydrogen here. So this guy should be a triplet. And do you have a triplet in that region? You don't have a triplet there. Do you see that? You don't have a triplet. So you take that one off. Does that make sense?
So we're looking at that region because it's a benzene.
Because it's a benzene ring. That's the benzene ring region. So we've taken off two guys. The only guy we have left is the one in which the substituents are para. Okay? Meaning on opposite sides of each other. And so we need to match and see. If I consider this hydrogen here, which is exactly the same as that other hydrogen, they are the same. They have the same environment. Does that make sense? What should be their multiplicity? Doublet. Is that okay? Should be a doublet. Now, if I consider this hydrogen, which is exactly the same as that hydrogen there, what should be the multiplicity? A doublet. And do we see it here? Oops. And do we see it here? Is that okay? So we see two doublets. So you see how we are already building our molecule gradually. And so we know we have a benzene ring. And then on that benzene ring, we know that there is a group here, X, and there is another group down here, Y. Is it okay, guys? Up to this point, are we good? So we know we have a benzene ring. There will be a group here, X, and there will be another group down there, Y. Up to this point, is everything okay? Okay? Now we need to identify X and Y. We need to identify them, X and Y. We need to identify them. Let's go now, let's move to the next region of the spectrum. Here. This is a doublet. And this is a multiplet or a sextet. It's a CH. Can you guys build that fragment? Can you see how the fragment will be? They are next to each other. Okay, we have two hydrogens that are equivalent. So, the only option I have that will be A. It means I will have my CH, which is this CH here, connected to two CH3. These two CH3 are equivalent. They only have one neighbor, the CH. That's why it gives me a doublet. Does that make sense? And now this H here will have 6 neighbors. That's why it gives me a multiplet. That's it. So we now have the three, we have all the fragments of the molecule. We have all the fragments. All the fragments of the molecule are an aldehyde. We have an aldehyde. We have a benzene ring that is disubstituted. And we have a CH with a CH3 there. So those are the fragments. Now we need to put them together. Does that make sense? And so you can easily see how they will come together. Right? You will see how they will come together. You can take this one and put it down there, and take that one and put it up here, or you reverse it. It gives you the same thing. Does that make sense, guys? Yeah. So at the end of the day, you will notice that the final structure for the molecule that will be the final structure for the molecule. Does that make sense? That will be the final structure, and now you can match those hydrogens. You can now match them, A, B, C, D, E. Remember there were 5 signals. This will give you 1 signal. This gives me the second signal, the third signal, the 4th signal, and that hydrogen, the 5th signal. Same thing with the carbons. How many signals do we have on the carbon? On the carbon NMR, we have 1, 2, 3, 4, 5, 6, 7. Let's see if we have 7 different types of carbons here. These carbons are the same. That gives you 1. This gives you 2. This gives you 3. This and this are the same. It gives you 4. That's 5. This and this are the same. That gives you 6. And that one, 7. Does that make sense? Yes.
Do you follow up to the first table?
Which first table?
Like, the one that, yeah, that one that brings.
So, I would highly recommend that you guys should solve problems from your textbook. At the end of the textbook, and all of you have access to a textbook. If you have a Mastering Chemistry account, then you have an e-text. And I will repeat myself again. I highly recommend you guys to solve problems from your textbook, especially this kind of problems that combine all the different spectrums. I will repeat that again. Solve problems from your textbook. This is the second time. It is a 25 question point in your exam. Solve problems from your textbook. Voila. Oh, you want to solve problem from your textbook? Yes, I repeat it again. That wasn't a question. Every time you go to the lab, you need your goggles. The best way you can do is you can keep your goggle in your drawer so that you will not have to worry about having goggles or not. Just keep it in your drawer, you know.